Okay, so welcome back to another video. So here we have an improper integral from 0 to infinity of the natural log of x divided by x cubed plus 1 then dx. So we have a natural log function and then a cubic polynomial in the denominator composed into our integrand. So some things we have a lot of techniques we'll be utilizing. So of course, what we're going to be doing is, of course, involving some u-substitutions. And then it actually converts that into some sums that we'll be using, actually specifically utilizing a geometric sum to convert all this out, and a couple of special formulas that we'll be utilizing to, get to the valuation we want. So this has nothing to do with this integrate, but I actually just realized that if you change the x cubed to an x squared plus 1, this wasn't posted on my YouTube, but instead on one of my TikTok accounts, that it applies that first step we'll be doing is, of course, breaking up the linearity and applying that u-substitution. And what happens from there is that it actually just cancels out the sum together such that the integrand of ln of x divided by x squared plus 1 is simply just going to equal 0. So I thought that was a pretty neat application, well, if you can call it that, but it just came into my mind to that realization that some of the steps we will be utilizing, well, that first step, but then afterwards it just gets a little crazy from out there. So with that in mind, so why don't we actually just jump right in? So we break up this, so we call this capital I. So we're going to break this up such that our bounds are going to start from 0 to 1 of our integrand. And then afterwards, we're going to have that it's just going to go towards infinity. So now we have 1 infinity ln of x divided by x cubed plus 1 and then dx. So our primary focus is taking a look at this integrand over here. Let's actually apply a u-sub. So I'll call this, we'll just say capital X. So let x equals 1 over u. So I differentiate, so that means dx is going to equal to -1 divided by u squared and then du. So with that in mind, we have to change our bounds, don't forget. So let's see, let me put a star for denoting this integral we're going to be changing. So 1 to infinity of ln of x divided by x cubed plus 1 then dx. Simply, if we perform the necessary changes, we have that as this approaches, so infinity for x, that means u is going to approach 0. Now I have 1, so u is going to be 1. Then we have now the natural log of 1 divided by u, and then all this being divided by, so 1 divided by u cubed, and then add this with 1, and then d, or not to say du, we have to replace this with -1 divided by u squared and then du. So with this in mind, of course, we have to switch our bounds, so that gets rid of the negative, and then we can multiply the u squared to everything under here. So I have a 1 divided by u and then plus u squared. But to fix that up so we don't actually have fractions under the denominator, let's just multiply a u to both the numerator and denominator. And taking one step forward, what we're going to do is we're going to apply some natural log properties. So we actually have a 1 divided by u. So apply the subtractions of natural log. So it's ln of 1 subtract the natural log of u. Of course, ln of 1 is just going to be 0. So that leaves us with a negative. So now performing all this out, we have this is going to be equal and then minus the integral from 0 to 1 of, now we have u and then times ln of u divided by u cubed and then plus 1 and then du. Okay, so with this in mind, we can now actually substitute this back into here. Of course, these being two different variables, that we can say that is a dummy variable that we can actually just, switch around with. So we can actually just go back into the world of x in this situation over here. So let me actually just denote this over here. So that means now our capital I so far is going to be the integral from 0 to 1 of ln of x divided by x cubed plus 1 dx, and then subtract with the integral from 0 to 1 of the natural log, or now we're going back into the world of x. So actually I forgot to say x, then times ln of x divided by x cubed plus 1 then dx, and to recombine it back together, it's under the same bounds. But let me actually also factor out ln of x back into here. So now our new integral we're dealing with is 0 to 1 of 1 minus x multiplied by ln of x divided by x cubed and then plus 1 dx. Here's a challenging integral that we're actually going to be dealing with. So let's actually note that we're actually going to apply a geometric series into here. So this is for, of course, x, the absolute value of x being strictly less than 1. What we can do is, okay, I'm going to write this as 1 divided by 1 plus x cubed. And we know that that's actually just the same thing as the infinite sum starting at n is equal 0 of negative x cubed to the power n, but if you put everything back for distribute the exponent, so it's going to be negative 1 to the power n, then multiply with x to the power 3n. Okay, so now with that, let's actually now substitute this back into over here. So now I'm going to put this arrow just for the substitution. So what we have is the integral from 0 to 1, and then now 1 minus x multiplied with ln of x, and then now times the summation of our geometric series that we actually just put in. N is equal 0, negative 1 to the power n, and then x to the power 3n, and then dx. So with convergence, we can actually just interchange these two together. Geometric series absolutely convergent. So now we have that this is going to be the infinite sum. Now put everything outside of that such that it doesn't have to factor with x. So we have the negative 1 to the power n in here. So now let's see, negative 1 to the power n, and then now multiply with our integral from 0 to 1 of x times to the power 3n, and then subtract x to the power 3n plus 1, and then multiply with ln of x and then dx. Okay, so here's some things we want to note. So of course, this is actually kind of a little bit, you know, of off-putting, since we have x dn, or x to the power 3n, and then minus x to the power 3n plus 1. That could have been easier if that was just the derivative, if we're trying to integrate that standalone, but we have a natural log of x over here. We had to multiply through, so that's not going to be as easy as you think. So what we can do is, there's something you want to notice here. So we know that the following definite integral from 0 to 1 of x to the power n dx, simply basic antiderivative, and then just evaluate the bounds. That's the same thing as 1 divided by n plus 1. So what if we actually now differentiate this in respect to the letter n? So if I differentiate this, of course, that means I have, so applying Feynman's trick, of course, this is just x to the power n multiplied by ln of x and then dx. Then that means differentiate both sides. So let me actually write in respect to n. Then if I differentiate this, that means I have negative 1 to the power, or negative 1 divided by n plus 1 to the power square. So with this in mind, we can actually notice that if we just put in the pieces together with our exponents, we can actually get something of this form. So now that's actually the next step we're going to be doing. So now the integral, so I'm actually going to put a star over here. The integral 0, 1, x 3n, then subtract x 3n plus 1, and then ln of x dx. Simply, in other words, if we actually, again, as mentioned, put everything back together, I have negative 1 to the power, or negative 1 divided by 3n plus 1 quantity square, and then add this with 1 divided by 3n plus 2, and then quantity square. Okay, and so now putting this back together, I now have that I is going to equal to the infinite sum, n is equal 0 of negative 1 to the power n, and then now just substitute this back into over here. Negative 1 divided by 3n plus 1 quantity square, add this with 1 divided by 3n plus 2 quantity square. So the next step is actually going to be something very interesting. So, and I'm not actually going to write this on the board. Instead, I'm actually going to, use the power of video editing to actually give you this demonstration over here. So notice that the following infinite sum, negative 1, so of course index starts at n is equal to 0 to infinity, of the alternating negative 1 to the power n, all this being multiplied by negative 1 divided by 3n plus 1 quantity square, add this with 1 divided by 3n plus 2 quantity square, subtract 1 divided by 3n plus 3 quantity square, is actually going to equal to the infinite sum with our index starting at n is equal to 1 of negative 1 to the power n divided by n squared. So you'll notice that if you actually take those two different series and expand that out, we're actually going to get the very similar terms. So what's missing, although, is that you have one that's missing for the negative 1 divided by 3n plus 3 quantity square term of that series coming from the earlier that we just derived, which is not a big deal because all you have to do is, as mentioned, you can actually use the negative, or you can actually use the infinite series of n is equal 1 to infinity of negative 1 to the n, and then divided by n squared. Then we just have to add the term for the infinite sum, n is equal to 0 for negative 1 to the power n divided by 3n plus 3 squared. And then as you notice that if you actually expand everything out, it actually comes into full circle and it actually equals each other. So using that sort of creativity and observation with those expansions, we can actually now provide a nice substitution we could actually use for our capital I. So that was a lot to explain, but hopefully this demonstration actually with the pictures that rather I just describe will make everything come into light. So with that in mind, so now substitute all this out. So now I have the infinite sum at n is equal to 1 of -1 to the power n and then divided by n squared. And then now we just add this with the -1 to the power n divided by 3n plus 3 quantity squared, that expansion. So just like this. Okay, and so with this, let's actually do a little bit more factoring. So 3n plus 3 is the same thing as 3 times n plus 1 of that quantity, and then all that being squared. So let's actually factor that out. So that means I have a 1/9 of that constant. So that means now this is going to stay the same for n is equal 1, -1 to the power n, and then divided by n squared. And then add this with 1 divided by 9 of the infinite sum at n is equal 0 of -1 to the power n divided by n plus 1 quantity square. Okay, and so what we'll do here is now let's actually change our index over here. So now equals, let's switch to a different marker for this one. So we're going to change our index over here, but also what I'll do is I'll actually multiply and divide a -1 over here. So what that'll do is that'll actually add to the base. So that means now subtract a -1 over here, but that sign will also become negative. So minus the infinite sum, n is equal to, or still just 1 of -1 to the power n minus 1 divided by n squared. And then now we actually just change our index over here. So that means plus 1/9. Then starting with our index at n is equal to 1, or yeah, 1 of now -1 to the power n minus 1 divided by n squared. And then if I just combine all this together, we have that this is just going to equal -8 divided by 9. So that's the same quantity, of course, or the same terms. So we're putting together. So -8 divided by 9 of our infinite sum at n is equal 1 of -1 to the power n minus 1 divided by n squared. And then what we'll use is, of course, notice that by this definition of the Dirichlet-Adolph function, which says that you have the infinite sum at n is equal 1 to infinity of -1 to the power n minus 1 divided by n to the power s for some s. That's the eta of s. And then another thing we'll actually be utilizing is its relation equation such that the eta of s is just going to equal to 1 minus 2 to the power 1 minus s, all that quantity being multiplied by the Riemann zeta of s. So as we notice that this is actually at s is equal to 2, so that means over here this is the same thing as eta of 2. And then to finish it off, so I actually just put in the back over here, so let me actually make some changes. So the eta of 2 is going to equal to 1 minus 2 to the power 1 minus 2, which is 2 to the -1, which is just 1/2, and then multiply by the Riemann zeta of 2, which of course that's actually just the Basel's problem, pi squared divided by 6. So that all just evaluates to just pi squared divided by 12. And so now I have that I is equal to -8 divided by 9 multiplied by pi squared divided by 12. And if you simplify all this out, you'll get -8 pi squared, or not simplify it, if you just multiply this first, you get -8 times pi squared divided by 108. Then you simplify this out, you'll get that the final answer is just -2 pi squared and then divided by 27. And so therefore that is our final answer to this improper integral over here. So just like that, simple, and you know, it's pretty cool. So there you have it. I already said it again, so I'll say it again. That's pretty cool if you ask me.